Welcome to CSIR JRF Physics class, Nuclear Physics, and this is class number 3, Nuclear Radius. We start with a question on nuclear radius. Nuclear radius. Nuclear radius. The radius of a 29 copper 64 nucleus is measured to be 4.8 into 10 raised to minus 30 centimeter. A part, this question has two parts. A part, the radius of a 12mg27 nucleus can be estimated to be A 2.86 into 10 raised to minus 13 meter, B 5.2 into 10 raised to minus 13 centimeter, C 3.6 into 10 raised to minus 20 centimeter, D 8.6 into 10 raised to minus 13 centimeter. അപ്പോൾ ഇവിടെ നമുക്ക് കോപ്പറിൻ്റെ ന്യൂക്ലിയർ റേഡിയസ് തന്നിരിക്കുകയാണ്. അതിൽ നിന്ന് മെഗ്നീഷ്യത്തിൻ്റെ ന്യൂക്ലിയർ റേഡിയസ് കണ്ടുപിടിക്കണം. അതിന് നമ്മുടെ റേഡിയസിൻ്റെ എംപിരിക്കൽ ഫോർമുല അപ്ലൈ ചെയ്ത് ചെയ്യാവുന്നതാണ്. The empirical formula for nuclear radius is R is equal to R0 A raised to 1 by 3. R0 is a constant, which is 1.3 Fermi, and A is the mass number. And when we apply this equation in two cases, that is for R magnesium and R copper, we get the ratio as A magnesium by A copper raised to 1 by 3, the constant R0 will cancel. That is 27 by 64 raised to 1 by 3. Therefore, R magnesium by R copper is equal to, the cube root is 3 by 4. Cross multiply, Rmg is equal to 3 by 4 into R copper, that is 4.8 into 10 raised to minus 13. We get a 3.6 into 10 raised to minus 13 centimeter. That is the answer. And this is another part question. The root mean square RMS energy of a nucleon in a nucleus of atomic radius A in the ground state varies as A raised to 4 by 3, A raised to 1 by 3, A raised to minus 1 by 3, A raised to minus 2 by 3. The energy, the root means square energy of a nucleon varies as. അപ്പോൾ എനർജിയുടെ ഇക്വേഷൻ ആണ്. അതിന് ഒരു എംപിരിക്കൽ ഫോർമുല ആയതുകൊണ്ട് ആ എംപിരിക്കൽ ഫോർമുല അപ്ലൈ ചെയ്താൽ നമുക്ക് കിട്ടുന്നത് സി എന്നുള്ള ആൻസറാണ്. എനർജി വേരീസ് as A raised to minus 1 by 3. That you have to remember. Next question, the difference in the Coulomb energy between the mirror nuclei 24 chromium 49 and 29 magnesium 49 mirror nucleus, they are isobar, the same mass number, different atomic number, is 6 MeV. Assuming that the nuclei have a spherically symmetric charge distribution and that E square is approximately 1.0 MeV femtometer. The radius of the 25 mn 49 nucleus is. അപ്പോൾ അതാണ് നമുക്ക് കണ്ടുപിടിക്കേണ്ടത്. ആൻസർ എ 4.9 into 10 raised to minus 15 meter, 4.9 into 10 raised to minus 15 meter. One is 13 meter, it is the second is 15 meter. 5.1 into 10 raised to minus 13 meter, 5.1 into 10 raised to minus 15 meter. The answer is B. When we express the nuclear radius in terms of meter, we get 10 raised to minus 15. So with that idea, the answer A and answer C can be ruled out because they are in 10 raised to minus 13. So 10 raised to minus 15 choices we have to select. So B and D are the possible choice, and on calculation we get answer B. And the nuclear radius in terms of energy is given. It is 3 square by 5 delta W into Z1 square minus Z2 square. The value substitute, we get 4.9 into 10 raised to minus 15 meter. Now, there's a question based on dipole moment of nucleus. A magnetic a nucleus has a magnetic dipole moment and also quadrupole moment. Here, dipole moment question. In the intrinsic electric dipole moment of a nucleus ZXA, increases with Z but independent of A, decreases with Z but independent of A, is always zero, increases with Z and A. Answer is D. Increases with Z and A. ഇനി ന്യൂക്ലിയർ പാരിറ്റിയുടെ ഒരു ക്വസ്റ്റ്യനാണ്. ന്യൂക്ലിയർ പാരിറ്റി. The ground state of 11 pp 207 nucleus has spin parity. Spin parity J star is 1 by 2, while the first excited state has Jp is equal 5 by 2. The electromagnetic radiation emitted when the nucleus makes a transition from the first excited state to ground state is E2 and E3, M2 or M3, as E2 or M3, M2 or M3. The answer is C, E2 or M3. For delta J is equal to 2, 3, there is no parity change. No parity change, delta J 2, 3. For even type, pi p is minus 1 raised to 1. For no parity change, I is equal to 2. For M1 type, delta pi is equal to parity change, minus 1 raised to L plus 1. For no parity change, I is equal to 3. I plus 1. I is equal to 3. Delta is equal to no parity change, that gives E2, delta J equal to 3. No parity change gives M3. So the answer works out to be C, E2 or M3. Next is a binding energy question. Binding energy question, a bound electron and hole pair interacting in Coulomb interaction in a semiconductor is called an exciton. Exciton quantum. The effective masses of an electron and a hole are about 0.1 ME electron mass and 0.5 ME respectively, where ME is the resting mass of the electron. The dielectric constant of the semiconductor is 10. Assuming that the energy levels of the excitons are hydrogen like, the binding energy of the exciton in units of Rydberg constant is closest to 2 into 10 raised to minus 3, 2 into 10 raised to minus 4, 8 into 10 raised to minus 4, 3 into 10 raised to minus 3. The answer is C. Solution. The binding energy of exciton is written here, 13.6 square into mu L by ME square, where mu is equal to MP into ME, the positron and electron. The particles given are, you look here, the particles given are electron, mass of electron, and hole. So MH. ME into MH by ME plus MH. That is the reduced mass mu. That one calculation we get that value. Therefore, mu by ME is equal to 0.0833. E is 13.6 eV. So put the values. 0.0833 by 100 is equal to 13.6 into 806 centimeter raised to minus 1 into 8.33 into 10 raised to minus 4, which is 9.14 centimeter. That is the energy equation. So E by RH, centimeter raised to minus 1. Energy we express in centimeter raised to minus 1. So E by RH is equal to 91.4 centimeter raised to minus 1 by 1.097 into, that is Rydberg constant, 10 raised to 7, 10 raised to 5. Centimeter Rydberg constant 5 ആണ്. Power 1.097 into 10 raised to 5 centimeter raised to minus 1, that is 8.33 into 10 raised to minus 4. The correct option is C. Next question. The binding energy B of a nucleus is approximated by the formula B is equal to A1A minus A2A raised to 2 by 3. Just 2 by 3, I think. Minus A3 into Z square A raised to, there is a quantity, minus A4 into A minus 2Z square A raised to minus 1, where Z is the atomic number. This is formula similar to the Weizsäcker formula. The Weizsäcker's Weizsäcker's formula. The atomic number and A is the mass number of the nucleus. If A1 by A2 is 30, the atomic number is set for naturally stable isobars. Isobars means constant value of A. 30A by 60 plus A raised to 2 by 3, 30A by 30 plus A raised to 2 by 3, 60A by 120 plus A raised to 2 by 3, 120A by 60 plus A raised to 2 by 3. The answer is C. 60A by 120 plus A raised to 2 by 3. And the calculation is given here. This is the sort of calculation we employ. You read it. And it you by heart the answer. Otherwise, you have to study all these calculations. We have to refer the textbooks to obtain this formula. This is the calculation. Next question. The binding energy of a light nucleus is, that is in ZA. Z is atomic number, A is the mass number in MeV, E is given by the approximate formula, the Weizsäcker's formula. B, binding energy of A is the element. A is the atomic number and Z is the A is the mass number and Z is atomic number. B is equal to 16A minus 20 A raised to 2 by 3 minus 3 by 4 Z square A raised to minus 1 by 3 plus 30 L minus Z square by A, where N is equal to A minus Z is the number of neutrons. The value of Z of the most stable isobar for a given A is, the four answers are given here. A by 2 into 1 minus A raised to 2 by 3 by 160 raised to minus 1. B is A by 2, etc. The answer is A. Answer given is A. And the formula is, when we write binding energy, we have to differentiate it and we have to find dou B by dou Z, dou B by dou Z and equate it to 0. Equate it to 0, then we get the value of Z equal to this. Now comes the actual semi-empirical formula, Weizsäcker's formula. Weizsäcker's formula. The Weizsäcker's formula for the binding energy in MeV of a nucleus of atomic number Z and mass number A is 15. 15 15.8A ഇത് ബൈൻഡിങ്ങൽ ഇക്വേഷൻ ആണ്. ബൈൻഡിങ്ങൽ 15.8a minus 18.3 a raised to 2/3 minus 0.71 into z minus 1 a raised to 1/3 minus 23.2 into a minus 2z square by a. The ratio Z by A for the most stable isobar of A is equal to 64 nucleus is nearest to A 0.30, B 0.35, C 0.45, D 0.50. So the Weizsäck's formula we have written the values of A Coulomb and A asymmetric A are given. Substitute the value and find Z by A. Find Z by A. We get 0.45. There is a partial calculation and the answer is C. Again, a Weizsäck's formula question. The binding energy B of a nucleus, mass number A and charge Z, that is atomic number Z, is given by this equation where the constants are given, you read it, and then for the most stable isobar for a nucleus with A is 216 is 68, 72, 84, 92. നമ്മൾ നേരത്തെ ചെയ്തപോലെ ചെയ്യണം. നമ്മൾ dB by dz 0 ഇക്വേറ്റ് ചെയ്യണം. ഫോർ മോസ്റ്റ് സ്റ്റേബിൾ ഐസോബാറിന് dB by dz അല്ലെങ്കിൽ ഡോ ബി ബൈ ഡോ ഇസഡ് 0 ഇക്വേറ്റ് ചെയ്യണം. അങ്ങനെ അപ്പോൾ ഡിഫറൻഷ്യേറ്റ് ചെയ്തിട്ട് അത് കണ്ടുപിടിച്ചിട്ട് 0 ഇക്വേറ്റ് ചെയ്യുക. എന്നിട്ട് സിംപ്ലിഫൈ ചെയ്യുമ്പോൾ ഈ കാണുന്ന ഇക്വേഷൻ കിട്ടും. അതിൽ നിന്ന് ഫർദർ സിംപ്ലിഫിക്കേഷൻ yields Z is 82.3. So there are number of formulae and we have to remember the Weizsäck's formula. In most problems, the Weizsäck's formula will be given, and for stable nucleus, stable isotope, isobar, we have to equate dB by dz to 0. For most stable isobar, you know, it is the nucleus having same mass number, different atomic number. And for a stable isobar, dB by dz is 0. We have to find dB by dz equated to 0 and find Z or A or Z by A. That is a method. Here Z is determined. The answer is 82.3. അപ്പോൾ Weizsäck's formula എന്ന് ക്വസ്റ്റ്യൻസ് ചോദിക്കാറുണ്ട്. അത് സ്റ്റേബിൾ ന്യൂക്ലിയസ് ആകുമ്പോൾ അതിൻ്റെ ഐസോബാർ ആകുമ്പോൾ അത് dB by dz 0 ആകും. അപ്പോൾ നമ്മൾ ഡിഫറൻഷ്യേറ്റ് ചെയ്തിട്ട് ആ ഡോ ബി ബൈ ഡോ ഇസഡ് 0 ആക്കിയിട്ട് അതിൽ ഇസഡ് കാണാം, എ കാണാം, അതുപോലെ ഇസഡ് ബൈ എയും കാണാം. That is all with your N3 class. We continue. Thank you.